In this lecture video, we're continuing the topic of crystal field theory with coordination complexes. So in this slide, we're looking at the difference between what is called high spin and low spin. And looking at these images, we can see that high spin occurs when you add your electrons first to the lowest 3 d orbitals and then up high, and then you go back in pair. And this will happen if your delta, or your crystal field splitting energy, is small. This happens if we have what is called a weak field complex. And how do we determine if it's a weak field complex, or, as we see over here, a strong field complex? We look at the ligand. Our ligand here is fluoro versus the ligand here, cyano, and we'll talk about that in a minute. So again, a small crystal field splitting energy, we first put the electrons down low, which is the same as Chem 101 and 60. But before we pair the electrons, we put them into the higher energy orbitals and then we pair. If we have a large splitting energy, which occurs if we had a strong field complex, which again is based on the ligand that we have what is called low spin. In a low spin complex, you first fill the orbitals singly, and then you pair the electrons before you go up high. The reason we do this is there's a certain amount of energy associated with pairing electrons. So if we have a small crystal field splitting energy, it takes less energy to put the electron up high before you pair it. If we have a very large splitting energy, it takes less energy to actually pair the electrons than to go up to this higher energy orbital. And so how do we figure out the splitting energy? We look at the ligands. And we look at what's called the spectrochemical series. In the spectrochemical series, we have a list of our ligands. So the list of the most common ligands in order of increasing delta. So I can see, and this is also on your study guide, so pull out your chapter 25 study guide, and we can see increasing delta. We have on the left-hand side small delta, which we call weak field. Which results in a high spin complex. And on the right-hand side, we have our large delta, large splitting energy, which is a strong field complex, which results in low spin. And in this slide, we're seeing that we have, so in this small delta, fluoro. So we have our fluoro ligand, which results in a splitting energy, as we see here. And then I can see my splitting energy is increasing as I go from one example to the next. And what is causing that is, again, the ligand. So I have fluoro, aqua, which is right here, amine, and cyano. And there's a cutoff that your text gives you, which is right between aqua and amine. So we will call from iodo to aqua our small delta, and from amine to cyano our large delta. And how does this affect the color? Well, remember our color here, green to violet to yellow, and then so again, we're still yellow, and that just means that we have a larger energy, but we're still in the yellow spectrum. And remember, we're looking at our color wheel. red, orange, yellow, green, blue, violet. Roy G. Biv, you may have heard that before. So if we see green, if it appears green, we're scattering green. That means we're absorbing red. And on this other extreme, if we're seeing yellow, that means that the wavelength scattered is yellow, and the wavelength absorbed, so our complementary color, would be violet. And remember the wavelengths of visible light. Violet has the shortest wavelength, but the largest energy. And our energy equals hc over lambda, just reminding us that energy and wavelength are inversely proportional. So our smallest wavelength gives us the largest energy, and that's what we see here. So our wavelength absorbed is violet, which is our shortest wavelength, largest energy, and our wavelength absorbed here is red, which is our longest wavelength and our shortest energy. Just as a reminder, their wavelength for red light is about 700 nanometers at the extreme, and violet is around 400 nanometers, just to keep that in mind. Again, what we're seeing here on this slide, the splitting energy changes based on the ligand that we have. In order to figure out the energy, you need to look at the spectrochemical series. I will give this to you on the cover of your exam, so you don't need to memorize it, but you do need to memorize the cutoff between my small splitting energy and large splitting energy. And also remembering our splitting energy, delta equals hc over lambda, and the lambda, let's add that little note here, it's always lambda absorbed, and we absorb and reflect complementary colors. We discussed that last time. So let's look at practice exercise 4. For which d electron configurations in octahedral complexes is it possible to distinguish between high spin and low spin arrangements? And what I'm going to do, I'm going to set this problem up for you and go over a couple of the configurations. I'll have you do the rest on your own, and I will have the answers posted on Canvas. To get started, let's consider D1. So if I have a D1 metal center, that means I have one d electron, and let's compare low spin to high spin. And I know I'm going to have low spin, they're going to stay down low if I have a large delta, high spin if I have small delta. So let me move this over. So in a D1 configuration, low spin, so 1, 2, this is my splitting energy. This is relatively large. High spin, I'll have small delta. So I like to put those orbitals very close together to remind myself how to fill them. So if I have a high spin, that means I'm going to first fill my low orbitals before I go up high. But if I only have one electron, that means I can't distinguish between low or high spin because I only need to use my lowest energy orbitals. Now let's look at D2. With a D2 complex, that means I have 2 electrons. So the first 2 go down low. And again, I cannot distinguish between low or high spin. If I have a D3 complex, so 3 electrons, again, low and high spin, exactly the same. Now let's look at D4. And we will start to see a difference here. So this again is my large delta versus small delta. So for large delta, low spin, I fill my electrons 1, 2, 3, and now the fourth, I pair it. Versus for high spin, 1, 2, 3, and my fourth will go up high. I'm going to go ahead and erase D1 so I can use this for D5 since I'm running out of space. For a D5 complex, so the first scenario where we have low spin, large delta, 1, 2, 3, and now I'm going to pair for my low spin complex. You stay down low before you go up high, so that's 4, 5. For high spin, 1, 2, 3, 4, 5. So going back to what the question is asking, for which d electron configurations in octahedral complexes is it possible to distinguish between high and low spin? So looking at D4, I can see when I have low spin and high spin, there is a difference. So which d electron configurations will D4? And we can see how D5. This is my low spin versus my high spin. We can tell a difference. And again, the reason that we would have either a high spin complex or a low spin complex, it's based on the ligand that would be given to you in the example, and you'd have to look at the spectrochemical series. So D1, D2, D3, that looks the same, right? Low spin, high spin, it's indistinguishable between D1 or D2 or D3. D4 and D5, we can see that there is a difference. And as you can imagine, D6, we will have a difference as well. So the first three go down low. Again, we're looking at low spin because we have large delta, 4, 5, 6. If I have high spin, 1, 2, 3, 4, 5, and now we pair. So in D6, I can distinguish between high spin and low spin. For high spin for D6, I can see I have 1, 2, 3, 4 unpaired electrons. And for low spin with D6, I have 0 unpaired electrons. Now let's look at D7. Let's make this D7. For low spin, my first three stay down low, and then I pair. And then my seventh goes up top. High spin, 1, 2, 3 down low, 4, 5, 6, 7. So again, I can distinguish, right? There is a difference. D7, I have 1, 2, 3 unpaired electrons if it's low spin. If it's high spin. D7, at low spin, I have only 1 paired electron. Now let's go ahead and look at D8. And again, I'm just going to erase these diagrams so I can reuse them because I'm running out of space. D8, high spin, 1, 2, 3, 4, 5. So I go up high first and then I pair. 6, 7, 8. D8 low spin, 1, 2, 3. I stay down low and pair because I have a larger splitting energy. So that's 2, 4, 6, 7, 8. And I can see that with D8, it's indistinguishable between high spin and low spin. I have for both of these examples just 2 unpaired electrons up in the higher energy orbitals, and the bottom are all filled. And you can see how if we were to go to D9, right, I would add 1 electron here. That would be indistinguishable. D10, that is the same. So in this exercise, we went over how to fill D1 through D10 low spin versus high spin configurations. And also we can see which D electron counts allow you to distinguish between high and low spin. Up until this point, we've only been looking at an octahedral crystal field diagram. So remember, for octahedral, our crystal field diagram, what we just looked at, 1, 2, 1, 2, 3, where we have all of the orbitals that are between the axes, degenerate and lower energy, and then our orbitals that are on the axes are higher energy. For tetrahedral, we have the opposite. So tetrahedral, we have 2 orbitals down low and 3 up high. And so if we were just to sketch that ourselves, the crystal field splitting diagram looks like that. Almost all tetrahedral complexes are high spin due to the reduced ligand-metal interactions. So that means for tetrahedral, we have to memorize this is going to be typically high spin. So for example, if I have D4, high spin, 1, 2, 3, 4, you go up high. And that's because, remember, in an octahedral configuration, all of our ligands are on the axes, so we have pretty high interactions. Tetrahedral, we have that 109.5 degree bond angle, so we have significantly reduced ligand-metal interactions, which results in a high spin complex. Lastly, square planar complexes, we have this configuration. 1, 2, 1, 1, 1. And the reason, as we go from octahedral, so remember in octahedral, this would be our dz squared, dx squared minus y squared, dxy, dxc, and dyz. And if we move from an octahedral to a square planar configuration, essentially what we're doing is just removing the ligands on the z-axis. So anything that has z character shifts down to lower energy because of those reduced ligand-metal orbital interactions. And this is why, with a D8 complex and a coordination number of 4, we typically have a square planar configuration. If we look at this, I can see 1, 2, 3, 4. It's usually low spin, 5, 6, 7, 8. So square planar, if I have a D8 metal, all of my electrons are paired. Let's look at the example if we have a tetrahedral structure and D8. Is there any increased stability? We know it's typically high spin. 1, 2, 3, 4, 5, 6, 7, 8. And so I still have 2 unpaired electrons, not much increased stability there. And this is why if I have a coordination number of 4, a D8 metal will be square planar because of this orbital diagram. Let's look at practice exercise 5. How many unpaired electrons do you predict for the tetrachlorocobaltate 2 ion? What we need to think about first is the coordination number, 2, our geometry, 3 our crystal field diagram. The splitting energy is going to be low spin or high spin. And 5, the number of d electrons on metal center. Let's look at this together. So I know my coordination number is 4 because I have 4 monodentate chloroligands. My geometry then can be either tetrahedral or square planar. I need to look at the number of d electrons on my cobalt 2+ ion. The reason this is cobalt 2+, each chloro is -1, that's overall -4 for all 4 chloros. I've got a 2- charge on my cobaltate complex ion, which means my cobalt must be +2, because +2 and -4 give us -2. So cobalt 2+, I look at my periodic table and I count across 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 minus 2, D7. D7, that means we're going to be tetrahedral. Our tetrahedral crystal field diagram is the opposite of octahedral. And I know tetrahedral is usually always high spin. So I don't even need to look at the ligand and the spectrochemical series. Now I can fill my d electrons in. High spin means that 1, 2 would go up high before I pair. 5, 6, 7. So that would be my crystal field splitting diagram for a D7 tetrahedral complex. And I can see that I do indeed have 1, 2, 3 unpaired electrons. You can follow these steps anytime you have a crystal field diagram problem. Lastly, we're going to finish up looking at applications of coordination compounds. So a couple examples here: extractions of metals from ores. So silver and gold can be extracted as cyanide complexes. And what we're doing, we're using the solubility of the complex ions to allow the ions to be either removed from solution or removed from a solid. We can use chelating agents in heavy metal poisoning, so EDTA can encapsulate that lead so it's no longer active, and also in chemical analysis. So qualitative analysis for metal ions, this allows us, by adding different ligands, we get unique colors to that specific metal cation.